Welcome, this is video 2 for the DC metering unit notes. In this one, we're going to begin by taking a look at how an ammeter will impact measurements on a circuit. Just like a voltmeter, ammeters will tend to influence the amount of current in the circuits that they are connected to. But unlike the ideal voltmeter, the ideal ammeter would have zero internal resistance. So remember that when it came to a voltmeter, to reduce the loading, we wanted a high resistance. The higher the resistance of a voltmeter, the better. For an ammeter, it's just the opposite. We want to have as low of resistance as we can, because we want to drop the voltage as little as possible so that the electrons can flow through it easily. Again, this is opposite to the ideal voltmeter. So let's take a look at an example. And again, this is an extreme example. So first, let's take a look at a circuit that has no ammeter. So in this circuit, we've got 2 volts of EMF. Resistor 1 is 3, resistor 2 is 1.5. So we see that resistor 1 is twice as resistive as resistor 2. If we go through and calculate the internal, or the resistance here, equivalent resistance I should say, we'd have 1 over 3 plus 1 over 1.5. We would want to invert that, and then if I calculate that real quick, I'd get 1 over 3 plus 1 divided by 1.5. The equivalent resistance equals 1 ohm. So the current would be 2 volts divided by 1 ohm, or 2 amps. So if we take a look here I got basically 1 1/3 amp going through this one. This is 2/3 of an amp going through that resistor. Remember, milli means thousandth, so it's actually 0.6 repeating. So obviously we got our 2 amps, and everything works out pretty nicely here. Now let's say we go ahead and introduce an ammeter, and this one has a relatively large resistance, 0.5 ohms. So if I put that ammeter, and if I'm using it to measure the resistance to this branch with R1 in it, notice that this resistance would be added to the 3 ohm. So now I have 3.5 ohms of resistance through this branch. And when you increase the resistance, you lower the current. So instead of having 0.6 amps, now I have 0.57 amps. Likewise, if I take that same ammeter and move it to the other side, I now have 2 ohms of resistance through this. I've increased the resistance, so that means I lower the current. So now I only have 1 amp of current flowing through that. And that's a pretty big deal, to lower it by 1/3 of an amp. That's quite a lot of amperage that's being taken out of that circuit. And also notice that if I lower the resistance of the ammeter, the lower that is, the less that will impact the measurement of the circuit. So one of the ways we have of reducing this effect, well, the first way is to use an ammeter that doesn't even connect to the circuit. Remember that when current flows through a wire, a magnetic field is generated around that wire. So what I could do is I could get a device that detects magnetic fields. I can place it around the wire, and remember that there's a relationship between current and magnetic field. The current is proportional to the magnetic field. So the stronger the current, the greater the magnetic field. So this device, when it measures the magnetic field directly, it's indirectly measuring the current. And this would be a non-contact ammeter then. And then it wouldn't matter what the resistance of the ammeter is at all. These devices right here, you can pick them up at any uh, box store, home improvement store. They're actually very, very common. And it's a nice device because you don't need to hook it up to your circuit to measure current. Other than the non-contact ammeter, then, for the ones we're going to be using, we just need to make sure that their internal resistance is as low as possible. That way we can minimize the effect of the internal resistance of the ammeter. Okay, the last topic I want to talk about in this unit will be a bridge circuit. And what bridge circuits do is they are used to compare two voltages. Think about a laboratory balance. If I want to measure something, how much something weighs or its mass, I need to compare that to some known kind. That's what a triple beam balance does. On a triple beam balance, you put something unknown on the plate, and then you compare that against some things that you do know. So we can do the same thing with electricity. Bridge circuits can be used to measure all kinds of electrical values, but we're going to basically focus on resistance. The standard bridge is called a Wheatstone bridge. And what it looks like is this diagram right here, where we have a power supply and 4 different resistors. We have 2 points that we're concerned about, point 1 and point 2. And what we want to do is we want to measure the voltage between points, between point 1 and the negative side of the battery, and between point 2 and the negative side of the battery. And basically, what we want to do is we want to then compare that between point 1 and point 2 themselves. So when the potential difference between points 1 and 2 is 0, the bridge is said to be balanced. So after we build this circuit, we would take a voltmeter and we would attach it to points 1 and point 2. And what we want to do is we want to measure this to get, we want this to equal 0. And that's what null means. Null means 0. So if I hook up a voltmeter between those 2 points and I get 0 volts, this circuit is balanced. And that basically means that the voltage drop between point 1 and negative and the voltage drop between point 2 and negative would be the same value. So if the voltage drop between 1 and 0 is 10 volts, and the voltage drop between 2 and 0, or I should say between 1 and negative, and between 2 and negative is, if they're both 10 volts, then delta V would be 0 volts. Now the bridge, its state of balance is solely dependent on the ratios of resistor A to B and resistors R1 to 2. It's also independent of the supply of voltage from the battery. That's really the beauty of it. It doesn't matter what voltage the battery is. Now, we're going to basically use the bridge to measure the resistance of something that is unknown. So what we would do is we would take something that we want to test, and we would place it either in for RA or RB. It doesn't really matter. The other 3 resistors then would be something that we would know. One of those 3 resistors is a special resistor that can change. I've got special boxes that you've got a dial, and when you adjust the dial, it changes the resistance of the box. And you would adjust that resistor until the voltage between points 1 and 2 are 0. When that happens, we can use this proportion to figure out what the resistance of the unknown thing is. And we'll be building some of these circuits in class to find the resistance of pieces of wire, unknown resistors, coils of wire, stuff that we don't know. All right, this concludes the notes on this unit.